You guys hear me okay? I knew Aaron could a minute ago. Perfect. So, per usual, some announcements. Today's obviously a little bit more of a lecture. Was not expecting a full class. We don't have a full class, so that's okay. We'll get a little bit more one-on-one or 1-on-12, something like that, 1-on-10. What do I need to hit up? Yeah, so Kanya was traveling over the weekend and said she could use another day. So I'm like, let's take up another lecture. I could use an extra day to kind of wrap up the Lambda calculus stuff. So we're going to do that today. I might have one more topic I'm going to cover tomorrow. I need to decide. It's on the Y Combinator, which maybe you guys have heard of. Besides being a big startup incubator, the Y Combinator is this really cool idea about how to get recursion where you shouldn't have recursion. And it's a really neat tool to have, but I don't think we're going to be able to get through it today because it's really complicated, and I need to come up with a better way to teach it. So we'll probably do that tomorrow. I think that's the game plan. It probably won't take the entire lecture. It very well could. And then we'll jump into parsing either tomorrow after that, tomorrow first thing if I decide not to cover it, or at the latest on Wednesday. And we'll cover parsing for probably 2-3 lectures, maybe might take 4 because we'll be doing a code along. So that brings me to, for those of you in class, we're back in class tomorrow. I have no idea if the TVs work or not, but we're gonna kind of play it by ear and figure out how to best handle that. So plan on being in person again. Maddie, Aaron, Kyle, if you're around, Conlon, if you're around, whoever else normally attends in person. I think that's the 4 of you or 5 of you. I maybe missed somebody. But anyway, we'll be back in person tomorrow. Same room, same time. What else do I need to hit? Oh, and bring your laptops in person. Obviously, those of you watching from remote land, you'll already have your laptops, so no worry about that. Next homework should be out sometime tomorrow morning. Getting caught up on that. My weekend was much busier than planned, but plan for that being out tomorrow sometime. That'll cover type checking. I'm catching up on email. A few of you emailed me about the midterm over the weekend. I guess they're in, Christina did get a hold of me about some problems with 2 questions. There's all of them, but 2 were okay, it looks like. If you had either of the 2 questions that kind of bugged out on us, I'm just going to strike those for everybody. So don't worry about those. Just fill out the midterm, submit it with those answers blank. Anything that had blank answers on this one, we'll just strike out. So it'll make grading kind of funky, but we'll deal with that later. So that's how you should deal with that. I'll probably send out an email saying something to that effect, or I guess it was already due, or maybe it's due at midnight. Yeah, so just submit that as is. We can't uncheck a box if it's been checked. Yes, that's okay. So like, I'm just gonna strike the question on the midterm, so it just won't count. Those 2 questions just won't count at all. I need to decide, because it's randomized, I don't know if those questions are on most of the exams, it'll be a free couple points. If not, we'll strike it, and the exam will be out of 2 less points. So if that makes sense. It probably doesn't, but I'll type all that up and it'll make more sense in writing. So just go ahead and submit it for now with those 2 checked. Just select any answer, that's fine by us. So questions about that? All righty, that's 1, 2, 3, 4. I think that was all of the things I needed to hit. Any questions before we get started? Anything that needs to be on my radar? Last couple weeks of class, I think today marks 2 weeks out, so wrapping it up. I'll just have, I think, the 1 more homework and kind of do some coding in class the next 2 days. Start wrapping things up after today. So anything before we begin? Oh, quick question for you guys. Are the fans that are behind me too loud? Or can you guys hear them at all? Can't hear. Perfect. Can't hear me or can't hear the fans? Hopefully you can hear me. If not, say something. Okay, perfect. Sweet. Yeah, if those do get loud for whatever reason, just say something and I'll lower them a little bit. It's kind of hot where I am right now. Sweet. Well, let's jump into it. If there aren't any questions, if there are, go ahead and throw those in Zoom per usual. So let's talk about numbers in the Lambda calculus. So if you guys remember, last week we worked with the Booleans quite a lot and played with those, got a little bit of a feel for the Lambda calculus and how it works. And it works in some pretty surprising ways. It doesn't feel like a normal way of programming, that's for sure. So we define true to be this structure. So it was two Lambda abstractions, or it's a function on two arguments, X and Y, where it selects the first argument. Similar for false, except it selects that Y, that second argument. That's just kind of a refresher. This is all fine and well, but how do we deal with something that maybe has more than one, or sorry, more than two elements? What if we need to select between more than one thing? More importantly, how do we represent the numbers? Something infinite like the numbers. And just the natural numbers for today. So this is going to be kind of a tricky question to answer. It's going to involve a really interesting kind of formulation. It's rather non-intuitive and hard to read when you first look at it, but it's really interesting once you kind of understand what's going on. And we'll spend a good bit of class just trying to understand the formulation. So can anyone remind me, how did we formulate, or actually, I'll just remind you. Earlier in the semester, we formulated the natural numbers like so. Not sure why I used double colons there. That's not proper in the Lambda calculus. We had a zero term. The name doesn't matter a whole lot, but we called it Z or zero. And we had a successor term. And that successor term had an inductive reference to itself, right? So the natural numbers are defined in terms of themselves. We had the zero, which always acts as a terminal. You always hit the zero eventually. And we use these numbers, obviously, to start building our interpreters, building out this lattice language from scratch. So we really started with nothing, right? And with the Lambda calculus, we're kind of back to ground zero again. We have nothing. All we have right now is the Booleans. We have Lambda abstractions, applications, and variables. How can we define the numbers, this infinite thing, without even, say, recursion? We don't even have recursion yet. Right? So this self-reference here, we can't use a trick like that this time around. What are we going to do? What do we have to work with here? We have three constructs we can work with. We have those lambdas, we have variables, and we have applications. So we have to use those. That's all we can use. I guess we could use binary and Booleans, but how do we represent multiple Booleans? I guess we could do kind of multiple argument functions. It's not a bad idea, common. But we're able to represent infinite numbers using just application, abstraction, and variables. And the trick is kind of non-intuitive. So I don't expect anyone to just pull it out of nowhere, unless you're kind of looking from the notes, in which case you're not really pulling it out of nowhere. So let's start talking about what the numbers are. So right off the bat, remember we need to represent these functions as some kind of function that takes more arguments outputs one. It kind of selects arguments is kind of the way we think of it a lot of the time. So we're going to define 0 much in the same way we defined true. Okay, and I'll give you this. This part's not going to be too bad. So we have lambda z, lambda s, z. Okay, and the naming z and s, arbitrary. Remember, those are just variables. They don't have any other meaning. But the name z and s are significant in some way. They kind of lead us somewhere and impart some meaning to this program. But on their own, they're just names. Okay, so 0 is a function that takes 2 arguments, outputs an argument. Okay, I'll call this function 0, and I'll write that note I just said. So, like for instance, z here is not the same as 0 that we just defined. Okay, can anyone guess how we might define 1? Using a similar format. We're going to take in a z, we're going to take in an s. How do we represent 1 here, do we think? Anyone make a guess? Yeah, there we go. So s of z, we're going to apply s to z. Right on. How do we think we define something like maybe 2? Any ideas for 2? Yeah, so we have s, sz, and you can imagine this keeps going on for something like 3. We have lambda z, lambda s, 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 z. Is this reminding anybody of anything? Here, I guess the parentheses will matter. So I should be a little bit more careful there. What does this remind you guys of? Yeah, it's exactly like our old definition of numbers up here, right? What's different though? There's one big difference. One big difference here. This part's certainly the same, but these lambdas aren't in the old definition. Yeah, and Colin just had it. So these aren't in the grammar-based definition, right? And that grammar-based definition doesn't really apply here, right? Ooh. Linnea, you might be on to something. If you want to elaborate a little bit, I'm happy to go down that rabbit hole. We're going to be going down that rabbit hole, I think. I think you might have had an intuition at some point. Ooh. So here, remember, we're not applying these. These are arguments. Try and elaborate more, Linnea, though, because you might have something there. I'm not sure. Otherwise, there might be a point of confusion, which we should elaborate on. I'm not sure. But keep typing. I'll give you a second. We also have, so if I wanted to say, okay, we have n, is there a way we could write this? So we have kind of a general form here. We have lambda z, lambda s, and then we have s, you know, and we have that, say, n times until we get to an SZ. That's our form, our general form, right? And that holds. Is this a sufficient definition, though? Are we allowed to write this in the Lambda calculus? Oh, right on, Linnea. Yeah, your elaboration is straight on. We're kind of defining them in terms of arguments. I like it. Can we write this kind of like, oh, do this n times in the Lambda calculus? Do we have a mechanism for that? I don't know is a sufficient answer here, actually. You guys don't have any idea. Someone might have an idea, though, so. Could we write that? Turns out we can. Requires just a little bit of a trick. Okay. Let me take a look at my notes real quick. I want to make sure I don't skip over anything. So the idea here is that let's look back at these definitions. Okay, forget the first half of that sentence. Here we take in a z and we take in an s. Remember, z and s are gonna be functions because all we have in the Lambda calculus are other functions. Some of those have names like true and false, but even true and false are functions, right? Z and s here are functions. So what happens, with z? Well, I don't do anything with z. Z is kind of that terminal again, right? It's selecting something, right? But it's still, in some sense, terminal. Now, what am I doing here? I'm applying some function s to z. These aren't necessarily static things. They could be other functions. Here, I'm taking in a z. I'm applying s twice to z, and so on and so forth. So it's really a repeated application now, if we kind of think of this in the Lambda calculus sense. So s and z aren't these static kind of constructors like we had before, but they're alive, they're functions. We don't know what they do, but they do something. Okay, so let's keep digging down that rabbit hole. Let's take a look. I need to jump a couple lines because he goes into a proof after this, and I don't want to go into proof. Let's take a look at the add one function. We usually call it successor. How do we define the successor in Lambda calculus? Well, what should the successor function take as an argument? You guys should all be able to answer this. What does successor take as an argument? A predecessor? That's kind of cheating, but what type of thing is it? Yeah, it takes another number, right? We'll call it n for now. We don't have types in the system yet. We could add types to this. We won't. It's not really necessary for what we'll study. And then kind of in just math shorthand, I'll change this. I'll write in red. We kind of just do an n plus 1, right? But we don't know how to do this part yet. That's going to be the tricky part. Now, how do I represent that in the Lambda calculus? Because we don't have any addition function, but how do I turn, say, this into this? That's the question we're trying to answer. But how do we do it generically? Okay, I'm going to give us the answer. We're not going to work this one out, but we are going to play with it a bit. So we have lambda n All right, and then it's giving out a new number. Okay. All our numbers always start with lambda z, lambda s. Okay, so we're gonna just copy and paste lambda z, lambda s. Okay, and I'll actually even change the color here. Hopefully that gray is noticeable. And I'm gonna write a little note here, because this is the form of numbers as we've encoded them. Okay, everyone with me so far? So we're just kind of copying that over. It's the form of number. That's how we do numbers, right? And if I'm adding 1 to something, how do I write that? How did we do that before up here? Using S and Z. How do I add 1 to something? Based off this form, what do I need to do? What ought to go right there? I have an N, I want to add 1 to it. What ought to go there? Let you guys think about it for a second. Ooh, really good question from Joseph. Joseph, I'm going to come back to that in a second. No, for now, it's not super relevant, but I'll address that as soon as we're done defining this. So hang on to that. Yeah, so Conlon says like define it recursively. We're not allowed to use recursion though. I like how you're thinking. Do I need to use suck there, successor, to do this? You know, when I go from this to this, what do? I don't use the function the +1 function we're defining now. What do? I take this S, right? Whatever is representing S, and apply it to Z, right? Or whatever I had before. So what might I do down here? Well, if I'm going to do +1, let's throw an S there, right? And then what goes inside of the application S? This is a bit more of the tricky part. Should I put a Z there? Does that make sense? Do people like that? What do you think? I'll let you guys kind of sit with that for a second. So Conlon says he thinks N should go there, right? Because N is the thing we're iterating. I like that. Good work. Sweet. I'm going to change back to white for this part. But I left some space there. What is N? N's a number, right? Do numbers take any arguments? So remember up here when we define 0, the form of 0 is expecting a Z and an S. Right? Same for 1, same for 2. Do we have an S, a Z, and an S that we could give N? Whatever N is? We do. We're just going to pass through this Z and this S. Now, why we do that will probably be more apparent in a minute when we play with this a little bit. There's a really good reason these stay around and we don't just put n there. Okay. Now, I wouldn't be surprised if most of you thought, what just happened, right? But let's play with it. Play with this, play with our intuitions a little bit and see if this works, okay? So if this function works, I should be able to write something like suck, 0, right? And we should get whatever should represent 2. Or we should get this right here. So I'll copy this over. Everyone with me that these should evaluate to the same thing? Let's test it out. Let's start evaluating it, okay? So successor is what? Let's start expanding it. We have lambda n dot lambda z dot lambda s dot s n z s. Okay, that's just copying the answer over. Nothing special there. This is that first successor. Or actually, even better, let's do the inner part first here. I think that should be easier for us. I'm going to color this. Keep track of it a little better. That's the pink part. This is the pink part. So that's from here. And then that's applied to 0. Okay. Let's make 0 blue. Remember, 0 is lambda z dot lambda s dot z. Okay. Everyone following along so far? Okay, so all I've done is replace those with their definitions. Okay, nothing super crazy yet, just subbing out for definition here. Okay, well, lambda z, lambda s, and z, they're applied to n. Okay, so let's sub it in to the pink part. So now, how do I want to write this? We'll for sure need a big equals over here. And I'm going to write a note in a color I haven't used yet. Let's just use orange this time. Sub lambda z lambda s dot z in for n. Okay, hopefully the colors help here. Nod yes if they do. Or type it in chat for me if the colors are helpful. Otherwise, I won't go through the trouble to do the colors, but maybe I will. I actually kind of like the colors. But so now we're doing that part. We still have the outer successor, even here. So we haven't touched the white part. But now we're subbing in the blue part for the pink part, or for n in the pink part. So now we still have lambda z dot lambda s. That hasn't gone away. Just the n has gone away. And we have s of n, okay? That is, I'm gonna run out of space here. That's okay. That's gonna be our blue part. So lambda z dot lambda s dot z. Let's see. And then applied are the pink z and s. Okay. Yeah, hopefully these colors, I think these colors are actually kind of making it work. Otherwise, this would be pretty hard to follow. Okay, so now what do we do with this? Well, we have an unhandled application there. So we can apply pink ZNS to this blue part, right? So let's do that. Let's just reduce this part. Pink ZNS, that makes these go away. We just get Z. Okay, so now the pink part, or rather, yeah. So now what we get is this. We have successor of lambda Z dot lambda S. Oh, that's supposed to be in pink. Lambda Z lambda S dot S. Okay, that's this one. And then this whole part in the yellow reduced down to just Z. Okay. That did the first successor. Let's do the second one. Okay, it's going to be pretty similar. I'll go a little faster this time, probably. So this time, let's go and change out. Oh, that definition, I'll just rewrite it. So now we have lambda n. I'll keep this in white this time. Lambda Z dot lambda S dot S of n Z S. Okay, that's the white part here. And we're applying that to the pink part again. And I'm just going to copy that over. Now let's start reducing this. First step.
Can you just scroll back up for just 1 second?
Oh, yeah.
So you.
Are you looking between these two steps?
The 2 steps above that. You just call that whole thing Z and bring it down?
So I'm not even just calling it Z. This reduces to Z.
Okay.
And the reason for that is, and maybe I went fast with that step. This Z gets applied here. This S is applied here. It selects Z as an output.
Got it. Okay.
Okay.
Thank you.
Cool. So really, I guess I drew a yellow Z. It ought to really be a pink Z if we're kind of being consistent. So I'm going to change that over. Because it's really the pink Z. If we're kind of keeping the colors all consistent, it shouldn't have changed. I'll leave the yellow highlighting there. Right, but that's what that computes. Back with me?
Yep, I'm tracking. Thank you.
Perfect, sweet. I think we're all caught up. I'd much rather write this all on a single line, of course, because this is kind of applied over there, but it's hard to with the big writing. So just know that those are applied together. We're applying the white part to the pink part. And I'll write a note to that. To pink part. And it's going to drive me crazy if I don't change those colors. So, okay. Now, this means we sub. I'll actually write this whole part out. We're going to sub lambda Z dot lambda S dot SZ in for the white N. What does this look like? This is the next step of our computation. And so we're going to copy over the long white section, duplicate. Perfect. And this N needs to become this. So let's just play some duplication game here. Make it nice and easy on ourselves. This will move over there, move that in, cut. You guys can't do this. I'll give you, don't worry, I'll give you a second to catch up writing. I'm gonna make actually the white part smaller instead of the pink part. So pink goes up there, and that'll have some parentheses around it, just like the last time. So very similar. Okay, now we can reduce a bunch of stuff. Oh, and the end's going to be gone because we applied that. So glad I didn't forget that part. Okay, so now we have this term. We can reduce this again, okay? So the white Z and the white S are going to sub in for the pink Z and pink S. So sub Z S in for Z and S. Okay, that's our next step because that's the unreduced part, right? We have an application here. Let's do that step. So now we have lambda Z dot lambda S dot, and that white S is going to stay there. And now we have Z and S in here. This is that step a second ago we were just talking about. We get that when we do the application and close it all out. Can we reduce anything else here? Or are we finished with our computation? Someone wants to refer back to what our original goal was. You'd have a very quick answer to this question. Conlon says maybe one more step. You might be able to make an argument there. But what are you thinking? Oh yeah, so Conlon's saying if we're fine with basically saying we could change this to 0, right? Which we won't, or sorry, we could change this to 0, which actually I'd argue we can't really do because this isn't the same 0 as that 0 up there. This whole thing, if we look up above, way up here, I ask, can we get this from the functions we just wrote? So from before, we said 2 is equal to lambda Z, lambda S, 2 applications of the S onto the Z. So I think we're done, right? We've effectively defined the successor function here, right? So I'll put a little square block. Boom, we've done it, okay? Successor works. It has the desired behavior according to the encoding we want. Now let's pivot a little bit. Oh, actually, before we pivot a little bit, I guess it is a pivot. I want to go back to Joseph's question. And this is a little bit of a segue. So question is, how is 0 different from true? This is a good question. So if we recall, we defined 0 as lambda z, lambda s dot z. We define false, sorry, we're not looking at false right now. We define true to be lambda x, lambda y dot x. Those seem pretty different to me, right? One gives you a z, one gives you an x. Those are different, right? Or are they? What do we think? Yeah, so Conlin's thinking they're pretty similar. I'd argue they're a little bit different, right? Because with like the successor one, it's not selecting between two things, it's selecting between infinitely many things. So here 0 and true are, well, I guess maybe you're onto something there. Yeah. So that's, yeah, okay. Conlin, I'll buy into what you said. It's applied differently. What do we mean by applied differently? So Colin said these are kind of applied differently. We don't end up ever subbing them out. So they are the same function. In the absolute sense. They serve the same exact purpose. Right? Arthur says he likes 0 and false are better analogs. I actually, Arthur, I only think you say that because 0 and false are equated with each other in machine numerals. I don't think, like, look at the Lambda definitions. I don't think they're better analogs because they're completely different functions. I think that's a bias from kind of hardware, right? But if you have more thoughts on that, please say so. So 0 and true are the same function. They behave the same way, but they're used in different ways, right? We could say applied in different ways, or maybe in different settings. So we definitely don't want to mix them up, right? Because that would be kind of like a type error. And in the Lambda calculus on its own, we don't have any type errors, right? So we still have to be careful about applying things where they shouldn't be applied. Later on, or sorry, we do have type errors. We don't have type checking. So we're not really diligent about our types. Ooh, Arthur, you had that's a really good point. So we want to keep them separate on our own. And it's going to be on us to do that. And mixing these up will have could have consequences. We need to be careful about it. Turns out for 0 and true, it shouldn't have consequences, but it may. Now, Arthur's point was from a conceptual perspective, both 0 and false constitute a lack of something. Arthur, I'm really with you, totally with you. False doesn't necessarily constitute a lack of something, though. It means precisely that something wasn't true. And there's a really subtle way that those are different things. And you could actually consult philosophers about that. It's a really deep question. But on its own, false actually represents an answer to a question, it just might not be as precise as you want. So if I ask you, you know, are you a college student? You would say either true, I am, or false, I'm not. But when you say false, it doesn't necessarily say you lack something. It just means it tells you a different fact, if that makes sense. And right on, we could have defined false as true with no consequences. We just have to kind of switch everything around, which there's an argument to be made that that was probably the better definition. For whatever reason, traditionally, that's not how we do it. And it actually might be so we don't mix them up. Because it's easy to mix up false and zero. It's harder to mix up false and one, if that makes sense, for functional reasons. So that was an interesting little discussion. I do like what you had to say there for sure. I wish I could write it all down, but you actually typed probably too much, more than I could write down quickly. So yeah, so that was a good little segue there. We're gonna want to keep them separate. Even though they behave the same, it wouldn't, you know, rock your world if you goofed them up, I don't think, as far as evaluating stuff goes. But we do want to keep them separate because we're nice, clean programmers. We don't mix up our stuff when we don't need to. Let's see. It'd be kind of like putting, if you only needed 1 and 0 for, say, a computation, it'd be like using true, like saying true plus true plus true plus true in C, which would be like 4, right? Which just doesn't, it works semantically though. There's like it's poor programming. Similar thing going on here. Now, why did we go to all this trouble to define this in this way? You know, it's great. We can build these things up now, but does it have any nice behavior? For instance, could we define something like the plus function? You know, can we write functions on the numbers? Can we define addition? Any initial thoughts? Anyone have any, like, something weird's going on in your brain? You're like, wait a second, we definitely can't define plus because of something Jack said earlier. Any thoughts? Said something at the very beginning of class that might be helpful here. Hey, there you go, Linnea. I said there was no recursion earlier. Arthur also, right there. We can't define anything recursively. So how are we going to define plus? This is an interesting problem. Let's explore it. Okay. How do I want to approach this? I could try and make a struggle to define it. Let's struggle to define it at first, and if I'll back up if we have too much trouble. Okay, so we can get at least some ways into defining plus for sure, right? For instance, how many arguments does it take? Could we write the lambdas at least? How many arguments do we need? What should we call them? Stuff like that. We could do at least that, I think. Ooh, so Conlin's may be onto something. We don't want them to call them S and Z because we're going to use those for the number kind of forms. So it's not a case kind of thing like before. So we're going to have, like, say, maybe some N and some K, and these are the things we're trying to add together. Yeah, so 2 N's, right? Just call them N and K, they're close. I don't know why we don't use M here. Let me think for a second. Oh, I think there is a reason why we don't use M here. We'll get to that in a second, though. Yeah, this is the tricky part now. So we have an N and a K. We brought that in. I don't think there's a good way for me to kind of lead you guys into the answer. So I'm going to produce the answer for you. And this is going to be one of those tricky things, and we'll kind of unpack it with an example. We're going to apply N to 2 things. Okay, so remember before, we had a base value when we were doing addition. So let's actually pull out our old addition function from the way we were doing it in the classroom before. So we had plus, we had a case for kind of z, the 0 case, and we had a y here. And remember that plus 0 and y was just y. Then we had the successor case, plus s of x and y was equal to successor of plus x and y. That was one way you could write it. The other way packed the s into the y term. So let's think about that for a second, right? We're trying to write this function, essentially, without recursion. How do we do that? So this is the tricky bit. In our encoding of the numbers, we did something very similar to how we encoded the Booleans. So if we go back up here, all the way up to the top, 0, if we think of these as selectors, they're selecting something. 0 selects the first argument, whatever we have. Maybe think of it as we're passing a function in that should be used when we see a 0. Does that square with everybody? So 0 selects the thing we should use when we have a 0. 1 selects the s, but applies it to the thing we should apply when we see a 0. Same here. So when we see a 0 here, and I apply n, okay, I'm putting n there, and n needs 2 arguments. This is the thing that corresponds to the 0 case. This is the thing that corresponds to the successor case, kind of like in pattern matching. In this function, what did we output when we saw a 0 for n? We gave it y. What's our y here in this example? Any thoughts? What's y? Y is our k. Okay, so we can think of n as saying I'm recurring on n maybe. Yeah, think of it that way, at least for now. And we'll replace this part, the 0 part, with k. If this doesn't make sense, bear with me. We'll work it. Work an example, and it should make more sense. For this s part, what do we apply when n's not 0? We're going to apply an s. Okay, but what do we call s? We call it that function, successor. Okay, so what does this say? You know, if we think about numbers and what they do, numbers take 2 arguments. It takes a function that we're supposed to use when we have a 0. And it takes another function that we're supposed to apply to that function when we have a successor or an s. Here, it's just going to be the successor function. Okay. So now let's apply this to something and make it a little bit more concrete. What happens when I do something like plus 0 and 1? Super simple. Let's work it. So here I copy, I'm going to expand out plus, because that's what's being applied. So duplicate this. And this is being applied to, wrong marker. This is being applied to 0 and 1. I'm going to leave those unexpanded for now. We'll expand those in a second. Everyone with me so far? Nothing about this confusing? I'm going to start coloring stuff though. So this will be, we'll make this, let's do green. Make this green. 0 can be, let's use purple. And 1 can be blue. Okay, now my next step. I'm going to apply zero and and 1 to n and k. Okay, that's the step I'm taking. So let's do that. So now in green, we have n and k. Well, those got replaced by 0 and 1. So we have n, that's 0. Wrong color. And here is 0. And we have k, that's 1. So 0 applied to 1 and successor. Everyone following along so far? Or are we lost? Doing good so far. Awesome. Okay, so now we need to apply 0. Okay, so let's expand it. We remember from before our definition of 0. Wrong purple. I'm using this purple, right? Yeah, same purple. Awesome. We had lambda z dot lambda s. Okay, and it selects for z. Okay, this is applied still to 1 and successor. I'll put a note, expand 0. Okay, can anyone jump ahead? What's this going to do? Can you finish this all in one step? So we're replacing 0. I saw the right answer in chat. 0 and, or sorry, not 0. Replacing z and s with 1 and suck. Okay, and I saw the answer. We should get 1 because 0, and yeah, Arthur elaborated very well. Because z is equal to 1, s is equal to suck there. So this whole thing reduces to that 1. Okay, this is analogous exactly to, not that case, this case right here. Right? Does everyone feel like that's similar? What just happened? Does anyone not feel that way? That would be maybe the more interesting way to pose that question. This was the uninteresting case. What happens if we do something like adding 1 and 1? Let's do that. So let's do a similar thing. Plus 1 and 1. Okay. Now, the best thing about this example is it lets me copy a lot of what we just used. So I'm going to copy all this bit. First step's almost the same. We're just expanding plus. And I'll write that note because I didn't before. Expand plus. Whoa, plus. Okay, that gets us a step. And then we're applying 0 and 1 this time. It's not 0, but it's another 1. So it's a purple 1 and 1. Give you guys a second to catch up writing. I'll put a big white line here. Different example. Okay. What can we do next? Well, we're just going to apply those up. So we have NK and successor again. So that same really is very similar again in the next step. So here we have 1, 1, and successor. Arthur's starting to catch on. Now, what's the 1 function? If we go up and look at it before, it would look something like this. So actually, I'll write a note. Expanding 1, the purple one. We will get lambda z dot lambda s dot s applied to z. Okay. And now the 1 and the successor part will stay the same. What should I do next? How can I further reduce this? Yeah, Linnea's got it. Replace Z and S with 1 and suck. Right on. So replace write this a little bit more efficiently this time. So we're going to replace Z, purple Z with something and purple S with something. Those will end up being Z replaced with 1 and S replaced with successor. Right on. So let's do that step. Remember, that's just the application, function application. So now we end up with, do we end up with any purple stuff? Doesn't look like it. So we're going to end up with successor and 1. And we already know what this reduces to. We could step through it, but it's going to be 2, right? We did this before. This step is exactly the same as that reduction we did up, way up here. Would have been this, right? Similar reduction, or rather it would be the same reduction as this step. This is 1, that's successor. So we already know what that should be. Sorry if I'm moving around a lot. So we're done. I'm going to skip that last step. I'm going to write yellow 2. Because this is reduction of successor and 1. Hopefully that last step didn't confuse anybody. So, oh, lots of stuff going on in chat. I like it. It's interesting. I'm used to working in math where inner gives outer, and I feel like in Lambda calculus we work outer to inner. You're not the only person to make that complaint, interestingly enough. Yeah, so I think you mean with respect to what we reduce first. And the reason for that is because there's this nesting thing happening here that unless you're doing really crazy math, you don't typically run into that. It would take really crazy math. But I think, I don't know, correct me if I'm wrong, I haven't solved an integral in probably 5 years. But in integrals, don't you solve the inner ones first, or is it the outer ones? I'm really racking my brain out because it has been ages. But yeah, it is kind of weird. And Arthur's answer, it looks like, or elaboration is right on. It's like every Z comes at the end, 2 possible outputs. The ordering of those right to left. Yeah, so then if I'm right, integrals would be similar to this, right? Integrals have a similar nesting structure, and therefore you solve out to in. Or sorry, inner to out. That would be inner to outer. Oh, I read your question the wrong way, Linnea. Sorry. Yeah, I see your point now. So you could kind of, the way we evaluate these, you could do it outer or inner first. It kind of, the way you solve this, there are tricks you learn as you go, and you can kind of tell how you should kind of do these reductions. As far as writing these go, I'm not great at writing lambda calculus stuff. It takes a lot of practice. And writing them is very kind of counterintuitive at the beginning. There is some kind of, I kind of see what you're saying. I'm going to reflect on that and see if I can give you a more thought out answer for why. Because I think you mean with respect to the evaluations. I'm not sure. But hopefully everyone with this example kind of saw what was going on. Is remember that that the constructors, successor and zero, are encoded in such an elegant way that they capture their own recursion principle here. So you don't actually need recursion. The constructors themselves capture that recursive idea. And that's what's really cool here, is that if this was a much bigger thing, what would end up happening is it would apply this to 1. But then if I had more numbers there, I'd have a stack of successors. Well, it's going to keep applying that successor function. This is why we had to pass way up at the plus function. Or sorry, actually, this is why, where'd it go? This is why way up here, when I kind of waved hands and said, okay, we're just going to do this part, this is why we had to pass the z and the s in. Is because here, in this case, that s is going to be that successor function. And apply that over and over again. Okay, I think I'm going to wrap up there. There's probably some confusion. So if there are more questions, throw those in chat. And I'm happy to stay and answer questions for a few minutes. Otherwise, I think we will actually cover lambda calculus probably all day tomorrow, because I think I do want to cover the Y Combinator. I think that would be a nice way to cap this off after covering how to write stuff like times and exponent. For those of you that are feeling really good with this, challenge for you, see if you can write the multiplication function. I'll give you a hint. It's very similar to plus, just like it was before, except you have to change some of the stuff you're applying here. So obviously, if we look at the plus we wrote right here, you're going to end up changing this k and the successor, but the end part will stay the same. Okay, so try that out if you're feeling good about this. And we'll pick up there tomorrow. Linnea asked, will we have recitation this week? Probably not, because we're not, the coding homework you're going to be doing will be for type checking from way back. So it'll be very similar to the interpreters. There's not really any more coding technique to do. But we will be kind of programming in class. So class will look a lot more like recitation the next few days with me. So, and Conlin, yes, we will be in person tomorrow. So I'll see you in class. Otherwise, if there are any other questions, I know some people popped in after I finished covering logistics stuff. So if you have questions, stick around. I'm happy to answer everything over again. Otherwise, have a great evening, and I will see y'all tomorrow. Same time, not necessarily the same place, I guess. But otherwise, have a good one, guys.